first conceptual model, what we call a mental model people have about groundwater is something like this. They think, well, here's a ground surface, okay, and there's a hole in the ground, and there is water here. Okay, trust me, you can try this. Go and ask somebody like a 12th grade student or even college students. Ask them to draw a picture of groundwater. What do you think they have? They literally have the first mental model they have is there's a hole in the ground. There's all filled, basically like a cave, underground cave or somewhere. There was water trapped, and then you can actually put this well here. So what is that a reasonable conceptual model? I mean, we're going to talk about this word conceptual model. Which is kind of a mental model. I mean, so part of the goal of this class is to kind of create a good, strong mental model of the system and then add physics to it or math to it, okay? So this is a basic conceptual model most people have, most common people have, okay? Can you tell me, is there a problem with this model? First of all, is this true? Yes or no? Okay. Now, if it is really, let's assume if it is true, is there a problem with this model? If there is a water body like this, there's a cave under the ground, where there's some trapped water body, is that of any use to us? Yes or no? Anything? You think?
No.
Why? That's the right answer, actually.
Soil above it will cave in.
Well, first of all, that's right. The load above would probably cave in. This thing would not probably sustain. Now, if there is a magic rock which created, and if it can take the load, let's say it can take the load, and it survived, still this particular water body will become useless for us because even if you drill and extracted this amount of water, then it's gone. It's a finite water, and you leave a hole behind. Okay, and then at least at that stage, definitely it'll cave in. Okay, so the idea of a groundwater problems usually is, first of all, you're looking for a resource which is renewable, okay, which means it's interlinked with something else. Okay, it's a continuous water body, just like a stream or an ocean. It's interlinked with something else. It's not an isolated water body. Okay, and there are perhaps some isolated water bodies available, trapped water, but they are useless for us. Okay, so we are always thinking about this big picture where this water is in contact with some nature, and it's a continuum essentially. Okay, so that's the first thing you want to keep in mind. With that, I mean the word groundwater itself it's pretty well. First of all, there is something about groundwater. Believe it or not, there is still debate whether it's a single word or two words. Okay, for all practical purposes, now the consensus is we would use it as a single word. So we will use in this class groundwater as a single word. Okay, but there are people who would argue that it should be two words. Okay, but so groundwater is basically a type of water body we are going to look at. Okay, simply by definition, groundwater is basically water in the ground. Okay. So if I used to do this experiment. Let's do a little mental experiment. If I had two beakers, one filled with soil, filled with soil, and one with water. Okay. And you got water and you got ground. You pour them together, you got groundwater. That's it, really. Okay. So you take a glass of water, you tip it in, then it becomes groundwater. That's by definition. And it's kind of a cool definition in a sense, because that definition right away throws this thing out, because whenever there is groundwater, there is some soil there, or rock matrix there, some matrix is there. It's always mixed with soil. Okay, so we're talking about groundwater always as a soil mixed with soil water system essentially. Soil and water are mixed together. Okay, so we need to think about how soil and water would be mixed and how they can exist together and in what way. Okay, so it's always a soil water system. That's the bottom line with groundwater systems. Okay, that's number one. Number two, and a simple mental picture of a groundwater I would like to do is that little McDonald cup she has. That's a good example of a groundwater system. You see that? So let's draw that. So here's McDonald cup, okay? And I would imagine you're filled with a bunch of ice cubes, lots of ice cubes, okay? And let's assume the ice cubes are like your soil body or a rock matrix, okay? So when the McDonald person dumps all the ice on the cup, you got soil essentially, okay, equivalent to a soil or rock, okay? Let's assume our magic ice won't melt, okay? So you got the ground, and then she pours her Coke, you got groundwater system, essentially it's mixed, and then the Coke will come somewhere here, and that's what it's a water level or groundwater level. That's it, basically, really, okay? So in a soil water mixed system, when there is some place where everything is saturated, that's what we're going to call the groundwater water level or a groundwater level, okay? And then eventually we're going to talk about head and all this stuff, but that's a model. And then the biggest structure we would ever build in groundwater systems is wells, okay? That's how we interact with groundwater system. What is the equivalent of well in my McDonald cup? That little straw poking out, right? That's my well, really. In fact, that's exactly what we do. We can either suck the water out, or you put the pump in and pump the water to the top, okay? So if you want to think about groundwater conceptually, the McDonald cup is it, actually. If you can understand everything in the McDonald cup and how water will be extracted out of this, because when you extract, the water level drops, right? The soil level doesn't drop. You only suck the water. So which means you need some sort of way to prevent soil from entering a system. What we use screen. We use a well screen to prevent water from entering from if it's a big rock matrix, you don't screen because the rocks don't flow, actually. So without screen, you can pump those system, rock matrix system, fractured systems, okay? So keep that in mind. Now let's put some numbers to this, because the minute you start mixing two phases, which is a solid and liquid phase. In fact, there are how many? Well, first of all, what is the phase? For those of you who taken geotech would have done this phase diagram, okay? But it's actually a very common sense thing. So don't worry about, don't stuck with terminologies and stuff. Phase is a different entity, essentially. In this case, ice cube is a solid phase, right? And the Coke is your water phase. And above the water level, there is also air. Okay? Or before the water came in, you had solid phase and an air phase. So usually it's a three-phase system. A groundwater system consists of three different phases. And from that, we can create these so-called phase diagram and define some properties. And we're going to do it in a minute, these things. But just again, if you keep this conceptual model in mind, everything will fall together easily. Okay, so that's a definition of a groundwater. Now, as I said, when we think about groundwater, this is a great mental model, but it's also a very small scale model. Okay, you're kind of viewing the system in a cup or a very, very tiny framework. So what as I said, in this particular conceptual model, the problem is, again, you're in such a small framework, you don't really think about how it will interact. So we're going to step back and see how the groundwater system is going to interact with the world and how is it all connected together. So here are some numbers to start with. Let's shift to this. Okay. So what we talked about, the very first question, what is groundwater? It's basically water available underground, which is mixed with some soil and water. Okay. So let's kind of look at a bigger picture of water in the Earth's environment, how kind of water is distributed, because that's important, because groundwater is not an isolated quantity. It's actually mixed with the rest of the hydrological system. Okay. So here's my so-called conceptual model. Okay. Keep in mind, everything is driven by solar energy, right? That's an ultimate provider. So the entire driver for moving water from one body to another body is basically solar energy. Okay, so you got the solar energy coming, driving our system, in the big picture. Okay, and the water is trapped in several parts of the atmosphere. Okay, one is the basic atmospheric water, where basically water is trapped in the clouds and the air phase itself. Okay, and there is also water trapped in what we call a hydrosphere, and the hydrosphere includes ocean water, sea water, lakes, rivers, etc. Okay, that's a water trapped in or stored in hydrosphere, and there is also some water trapped in the lithosphere, and that's where the groundwater comes in. Okay, lithosphere, litho means ground basically, or earth. Okay, and they're all in constant interaction with each other. For example, hydrosphere, ocean water evaporates, right, and forms atmospheric water, and then it starts to rain, and the rain, part of the rain can fall on the ground and become groundwater. Part of the rain is can be falling straight on the ocean or the river and become the ocean water, or a river water, or a runoff due to river water. And then the transpiration and evaporation from the ground, plants would transpire water, and then you form clouds, basically transpired clouds, and evaporation can lead to cloud too. So it's a very interlinked system. It's not an isolated water body. Okay, so you change at one place, you're going to basically influence the water budget in other places. Okay, so it's a mixed system. Okay, so if you look at the water balance over the entire world, groundwater is an important resource because about 97% of the water is in the ocean. Okay, so it's all salty. They're useless. Well, they're useful, but we can't drink it, essentially, right? It's unless we spend a lot of money to desalinization and things like that. So about 3% of the water is a fresh water. And if you look at the budget of the fresh water alone, about 98% of the about 2.34 of this 3% of the water is actually in the ice cap. They're all locked, basically. Okay, polar caps and stuff like that. So we really, look at it. We are actually left with roughly 1% of water, which is actually fresh water, which is kind of usable. Okay. Now, among this available fresh water, 98% are actually of the available fresh water is actually as a groundwater, and only 2% is in the lakes and rivers. So there is enormous amount of freshwater body available as groundwater, which is kind of not obvious, right? When we think about freshwater, we always think about lakes and reservoirs and rivers and stuff. That's only 2%. Okay, so if you really want freshwater to be utilized, about 98% is groundwater. Okay, there is one catch, however. The surface water bodies like lakes and rivers etc. They are renewed at a much frequent cycle. Okay, because river flows are faster, whereas the groundwater flows are a lot slower, so they are not renewed at a higher frequency. Essentially, the movements are very slow. But that should give you an overall picture of water balance. Okay. Now how do all these things interact? Well, that's what we call a hydrological cycle. So here's a conceptual model of which probably you would have seen in other classes, how all these three entities are linked together. Okay, so you got this a big lake or ocean or whatever you want to call, some sort of a surface water body, and then when it rains, part of the water actually penetrates ground, right, or soaks into ground, and it goes through what we call an unsaturated zone. We'll talk about what is an unsaturated zone. And then it goes through what we call a saturated zone, and we'll again define what is a saturated zone later on, pretty quickly actually. And part of the water could be captured from a well, actually. We might extract water from the well, but eventually all the water goes towards some sort of a surface water body. Okay. In fact, I'll show some data later. A bulk of the river water could be from groundwater. Groundwater is discharging into a river. A substantial amount of groundwater actually discharges into ocean. It's called subsurface groundwater discharge, actually. Okay, and if you, for example, if the people have drilled deep wells in Dauphin Island, which is way offshore, and you can still hit freshwater body because there is substantial discharge from the Mississippi Delta under the ocean, discharging into the ocean, essentially. Okay, but the point is, every drop of water which falls on Earth eventually goes towards some surface water body, and which is the largest surface body is ocean. So eventually it's discharged into the ocean. Okay. Okay, so that's kind of the big picture of hydrological cycle. And in this course, we are going to focus on just this groundwater body. And in fact, we are going to focus just below this surface, which is called the water level or groundwater surface, essentially. Now, there is substantial water trapped above unsaturated, above the groundwater level. It's called unsaturated water. It's also groundwater, okay? And we'll talk a little bit about it. But if you really want to learn that, there is a course in the soils department called soil physics, and they actually deal with just this region. Okay, and you can, and that's a very important region, obviously, for several reasons. So if you want to pursue some research around that area, then I would definitely recommend you should take one of those classes. Okay. Now let's put some numbers to these things. So what I'm going to do is I'm going to take a core sample somewhere here. Okay, let's say I drilled a well and took a little core somewhere here, a box somewhere here. Okay, and then I'm going to take that box and slap it on a little conceptual. This is my conceptual box. Okay, so I'm drilling right down here until I hit my water level, okay, and I'm going to lay it out here. So to start with, what I have, so when I start drilling, to start with, what I have is what we call a root zone. Oops. What I call a root zone, okay, so that's my land surface, and I started digging. The first thing what I have is a root zone, okay, and once we pass a root zone, what we have is an unsaturated zone. And why is it called unsaturated zone? We'll talk about in a minute why it's called unsaturated zone. And then there is another name for it. It's called vadose zone. So, and then you hit this so-called water surface or water level. Okay. Now again, think in terms of your McDonald cup. Okay. So if you had so that's why the McDonald cup analogy is a great way to think about this problem. So here are my ice cubes. Okay. Okay. As I start pouring Coke into it, it'll stop somewhere here. Okay. And this is what I'm going to call a water level or groundwater level. Okay. Now, by definition, below this groundwater level or saturated water level, what you have is basically solid and plus water. Okay. Now above the water level, what you have is a little bit of water. Okay. Now in McDonald cup you can't really see that, but in soil you can see the wet soil, right? Plus soil plus air. Okay. So there are three phases. Okay. Whereas below the water level or below the saturated zone, there are only two phases. Two-phase system. Okay. So now let's look at this. So and that's what when the system becomes a two-phase system, that's what we call a saturated zone. Okay, because it's saturated. By saturation we mean we just eliminated all the air from the system. Okay. So this is a saturated system. This is my unsaturated system. One is a three-phase system. One is a two-phase system. Okay. And so we're going to call that as a saturated zone. That as an unsaturated zone. And there's a little bit of zone called capillary zone, and we'll talk about that later. Okay. So let me put a few more definitions here. The unsaturated zone, as I said, is a three-phase zone. So you got solid phase, water phase, and an air phase. And the saturated phase is a two-phase zone. You got a water phase and soil phase. They just mixed with water and soil. Okay. So now what I'm going to do is I'm going to take a sub-sample of the system. Let's take a soil sample from an unsaturated zone alone and divide into these three phases. So I'm going to take this unsaturated sample and then divide these three components or phases into the system. So I can define some numbers, okay, to explain this. Okay. So here's my unsaturated zone, unsaturated sample. This is the sample above the water level, right? This thing. And so I'm going to take, somehow magically separate them. I'm going to take the soil separately, water separately, and air or gas separately, and then stack them up. Okay, this is just a conceptual thinking, right? So I stack them up. So and I'm going to I can define this in different units. Okay. On my right, I'm putting in terms of volume units. So I'm going to call Vs is the volume of the soil, Vw is volume of the water, V gas is the volume of the gas or volume of air. Okay. So this side is the volume of the different phases. Okay. Now the volume of the gas plus volume of water is called Vv is called volume of voids or volume of the holes in the, okay, and then everything added together we're going to call as big V, which is the total volume. Okay, and in terms of mass unit, okay, or weight unit, you can on your left hand side you can say, well, the mass of the gas is almost zero because there is very little gas in the system. And then mass of water is mw, mass of soil is ms, and when they add all together, I'm going to call it as a mass of the total mass of the system. Okay, is that clear? It's just a conceptual thinking, right? It's nothing magic about it. It doesn't show up all that well. Okay. Now, if I took my well, let's go back to my McDonald cup, right? I took my McDonald cup, okay. I basically take all these solid mass, right, and that is one stack. That is my or ice, basically, right? And then I can take the Coke volume or mass, stack it up. Okay. So that's how this below the Coke level would look like, right? Above, how does it look? Well, I'll have ice. Above that, I'll have just air. Okay. There is very little water will be there. Okay. Whereas if you have a soil water system, then water will stick to soil. There is some amount of soil. So that's what we're talking about. Okay. So that nothing strange or nothing complicated here. Okay. So now once I did that, I can put some formulas together. Okay. Now, let me tell you, people get frustrated with this phase diagram and phase formulas because they try to memorize formulas. You should never do that. You should just think of a Coke bottle. Everything should fall together automatically. You don't need to remember any form. We are going to derive some formulas, but literally you should not be. There is no need to remember any formula. This should be coming straight out of common sense. Okay. So let's put some common sense together. Okay. The first definition is called porosity. Okay. So when we talk about soil, the first property of the soil is called porosity of the soil. What is the porosity of the soil? Well, porosity is nothing but the void fraction. How much amount of hole in the ground? What is the percentage of the hole in the ground? Okay. And it's a dimensional quantity because it's a ratio, so it doesn't have any dimension. It's some sort of fraction. Okay. So let me before we do this, what is the porosity of rock? If you have a solid rock, what do you think is the porosity of it? Richard, right? Who's
Richard.
Okay.
I'd say 0.
Rock 0. Anybody else? Okay. What is the porosity of soil would be roughly?
Just the soil or everything?
Just any soil.
Like it's a solid part of it, or?
Well, we define porosity as a property of soil matrix. Okay. So if if I went out and took some dirt. Okay. So, okay. What's the porosity roughly?
I don't know.
Okay, that's fine. That's a very valid answer. That's fine. What is the porosity of your McDonald cup before she poured some Coke into it? You think? Okay. Anybody else want to refute her?
I'd say like 0.4 maybe.
Yeah, it's definitely not 0. Then what happens if it's 0? Let's assume. I need to get some names here. Okay, so I can pick on you guys. Megan, right? Steven. Min? M-I-N? Okay. I'm going to pick on you three today. So yeah, we'll rotate around. Okay. So I can learn the names too. No, I can pull her too into the discussion.
Amelia.
Amelia. Okay. Okay. So Megan said what? She said like porosity of our McDonald cup is 0. Okay. Well, what's the ramification? If it's really 0, Amelia, what do you think her problem is? She goes to the Coke counter and the girl or boy fills the Coke with ice cubes, right? And then I asked her what's the porosity. It said 0. Now it can be 0 under certain condition. If it is indeed 0, what's her problem, Amelia? What do you think? Does she have a problem?
There's no ice in it?
No, I said like so. She goes there and hits the ice thing and fills it with ice. After that, what is the porosity? And she said it's probably 0. What's that? There is air there. What is it? Can you guess the porosity? She guessed the porosity to be 0. If it is really 0, what would be an issue? You can't put Coke in it. So you paid $1, bought ice. You can't put Coke in it. So it better not be 0. Right? So now it can be 0 if we have a solid ice, we have a core of ice, poof, dropped it, then it is indeed 0. But then you are in trouble. You paid $1, got a brick of ice. Right? So porosity is an important property of a soil water system. Okay, that's where water resides. Okay, so first number I want you to put roughly is porosity. If somebody asked, hey, what is the porosity of anything? That doesn't matter, Coke cup or soil or rock or frac, just say 0.4. It's pretty close most of the time. And you will prove it yourself. In fact, one of the homeworks you will do is you will prove yourself that it's a magic number, but it's really not magic number. It's a mathematically deducible number. Okay, so now there are some exceptions. We'll talk about those exceptions. Okay, but if anybody asks, I think Richard's the one who threw the number. The one thing I want to learn is if anybody from this point ever asked you what's the porosity of, put anything you want, 0.4, it works most of the time. Okay, so put that number in your mind. Okay, and we'll prove it actually. That's a reasonable number. So what is that 0.4? 0.4 what? What unit it is, Richard? 0.4 of milligram, kilogram. It's a dimensionless quantity. It's 0.4. That's it. You can stop it. It's 0.4. It's a fraction basically. Okay. It basically says if I had 100% of something, 100% volume, it's a volume fraction, volumetric fraction. So if it's 100 ml of space in the cup, basically, if it can, without ice, if it can hold 100 ml of Coke, with ice, it can hold how much? Amelia. Sorry. Okay, so the porosity, we agreed that it's about 0.4. It works for everything. Okay, let's assume our Coke cup is also about 0.4 after filling the ice, right? So let's assume that the volume of our cup is about 100 ml. Okay, now what do you think? How much Coke do you think she'll be drinking today, if that's the case? 40 ml. Okay, so porosity directly tells you how much water is in the system or how much Coke is in the system. Okay, it's about 40%. Okay, and it is not a mass-based calculation. It's a volume-based calculation, volumetric calculation. Okay, so keep that in mind, and then now let's think about this problem. Okay, so the first thing we're going to first formula we're going to derive is the porosity of the soil. By definition, porosity of the soil includes in a three-phase system, because we are talking about unsaturated system, right? So far we are talking about two-phase system, which is ice and Coke. But if you had a soil there is a little bit of ice, a little bit of water, a little bit of soil, a little bit of air. So it's a three-phase system. So the porosity of soil would include the gas phase and the water phase. Okay, so that's the void, total void, which is VV the gas and water, VV, divided by total volume. Okay? So in our case, it will be 60 ml of ice and 40 ml of Coke. So 40 by, wait a minute, total volume. Total volume is 100. So it's 40 ml of Coke divided by total volume, it's about 40%. Okay? Okay, the next definition we commonly use is volumetric water content. Okay, volumetric water content of an unsaturated soil, which is a three-phase system again, okay, is by definition is volume of the water by total volume. Okay. Now, as I said, we are dealing with an unsaturated system, right? So we got air, water, and soil all mixed together. Okay, but we ignore, when we define volumetric water content, we ignore the air phase. Basically, it's a volume of water divided by total volume. Okay. Now, what is the volumetric water content? So here is my McDonald's cup, right? So what is the volumetric water content or Coke content of this cup here? What do you think? So this would be volume of the Coke divided by total volume, right? What do you think it is here? 0.4. Who said that? Thank you. 0.4. Okay. So the volumetric water content of a saturated system, when things get saturated, it becomes what? Porosity. Okay, because entire porosity is filled with Coke. So the volumetric water content kind of relaxes to porosity under the saturated zone, when the zone gets saturated. Okay. So that's what I'm trying to explain here. Okay. So the note, the theta V, which is the volumetric water content, will be going from 0 to n. N is the porosity. That's the definition, right? So it can go only from 0 to 0.4, roughly 0.4. Okay. When is it 0? What is the volumetric water content, Coke content here? 0, because there is no Coke there. Okay, but still there is total volume. So if it's completely empty, if it's just ice, then the volumetric water content, Coke content is 0 there, really. Okay. So it can go from 0 to n, so or 0 to 0.4, roughly 0.4. Okay. Now when it becomes 0.4, volumetric content becomes 0.4, that's what we call saturated. Everything is, entire void is taken. Okay. Now these are all completely definitions, so don't get, just use your common sense. Okay. There is another unit is called saturation ratio. Saturation ratio is RS, which is defined as volume of the water divided by volume of voids. Okay. So it's what fraction of your void space is filled. Now it's basically similar to the water content or volumetric water content, except it's now a fraction which goes from 1 to 0. Can you see that? Just think through it a little bit. Okay. Because now here we can operate with the total volume. Here we are operating with the void volume, so maximum can be only 0.4. So that gets normalized. So it can only go from 0 to 1. So when the saturation ratio 1 means the system is saturated, okay, which is also same as volumetric water content of N, which is equal to porosity. Okay. Now why do you need all these? Well, we're going to use all these parameters to define the soil properties later. Okay. Okay, so in terms of mass basis, we're going to define a few things. The first thing we're going to define is what we call dry bulk density. Okay. What is dry bulk density? Well, let's go back to our Coke example. Okay. Dry bulk density is you take the soil and dry it. Okay. Obviously, you can't take the Coke can with ice and dry it, unfortunately, right? But let's assume that it's a non-melting ice. I got a magic ice, or Megan has got a magic ice in her cup, which is not going to melt. Okay, so and so if you think about that, the solid alone essentially. So if you take the solid alone in this cup system, what is the density of the system? That's what we call a dry bulk density. So you take the soil, dry it. How do we do it? You put it in the oven actually, and dry it and weigh it, and you get the measurements. And it's usually defined by rho b. Dry bulk density is usually, it's got a symbol rho b. It's basically mass of the solids divided by the total volume of the solid. Okay, it's got a unit now. It's a dimension, mass per volume, and typical unit is kg per meter cubed, or pound per cubic foot. And I never have an intuition for pound per cubic foot, so I'm going to stick to the SI units. Now another number to remember. So the first number you remembered is what? Porosity is roughly what? 0.4. Okay. The second number to remember is typical value of bulk density is 1600 kg per meter cubed. Okay. Now that's kind of an odd. So if you're comfortable with gram per centimeter cubed, it's 1.6 gram per centimeter cubed. Now they're both a little bit odd numbers. The best way to remember them is, what is the density of water? What's the density of water, Richard? In this unit, kg per meter cubed or gram per 1,000. Everybody knows that, right? So the density of water is roughly, not roughly, it is 1,000 cubic meter per kg per meter cubed. So, is this still working? Okay, good. Sorry about that. Not going to drop anymore. Okay. So that's your reference. Okay. Always think in terms of water. Okay. Water is 1,000 kg per meter cubed, or it's 1 gram per centimeter cubed. So if you take a little centimeter cubed of water, it's about a gram. You can kind of feel for it, right? If you take a meter cubed of water, then it's 1,000 kg. Okay. So we know that. Now, instead of water, if you take this meter cube of box and empty water and fill it with dry soil, would it be higher or lower? It has to be higher, right? It's got rock in it. Soil is basically rock, comes from rock, right? Crushed rock. So from that, it should be always about 1,000. Okay. And it's about 1,500 or 1,600 per kg per cubic meter. Now, what is the equivalent pound per, anybody has these numbers, right? Pound per cubic meter? It's, I think, yeah, it's like 120 or something, pound per cubic. But I'm going to stay away from that, okay? But I know of some geotech calculation, you guys need this, but I'm going to stick to SI unit. But it's really important. You say, for example, I was sitting in a geotech testing lecture, not a lecture, geotech MS seminar. And this guy was doing some sort of consolidation test. So you got some soil and pounded it, and you get the Proctor curve with density of the consolidated material with time. Okay. Now I kind of looked at those numbers and said, and he was like, his numbers were like, it was in a pound per cubic foot, like 170 or 180 pound per cubic foot. And I quickly converted it, and it was pretty high, okay. And then he said, well, when I got this before pounding, it was some number, okay. I converted it. It was close to 900 kg per meter cube, which is just not possible, okay. So when you create numbers for density, always use water as a reference density. And if it's going below water, you screwed up something, obviously, okay. Now, what would be the upper limit on this? What do you think will be the upper limit on this number? So the lower limit of any soil water system would be 1,000, which is water density, right? Is there upper limit we can put in? Density of rock, okay? So no matter how hard you would pound, do you think you can exceed the density of rock? You better not. So this guy's Proctor curve exceeded rock density. And he kept hammering, saying that, oh, I used this, I pounded. No, you can't. You can't pound enough to cross the rock density. Or you cannot make it loose enough to cross the water density. Okay? Unless, using some foam material or something. So the next thing is, that's what is called particle density, or soil particle density, which is nothing but rock density. So if I took the particle alone, just ignore the voids, and took the particle alone, or the material which particle is made of, then its mass of the solids divided by the volume of the solid, which is called rho m, or material density, or mineral density. And the typical value of that is 2,600. That's rock density, kg per meter cubed, or 2.66 gram per centimeter cubed. Okay. Now here's your first trick question. Okay. If I had a rock which has got a material density of 2.66, let's do something else. Let's say if I had a rock which has got a material density of somewhere around that's 2.5 gram per centimeter cube, okay, and if I then crushed it and made soil out of it, okay, what do you think that soil density would be? Same as what? 2.5? Anybody else want to?
What's my air mixed in now?
No. The minute I made it soil, I created air into the system, right? When I had a rock, there is no air there. Okay? The minute I made it as a soil, the density drops to this. You see that? Because what I did, if you have a block of rock, that density will be 2.66. Okay? Because I'm talking about now the volume is the rock volume essentially, right? If you crushed it, the volume will go up because air will get in. Okay, so you got a bigger volume to deal with, but it's the same mass really, because air doesn't have any mass, and that's the reason it reduces to about 1.6. So there are three numbers I want you to remember. Porosity is roughly 0.4. Density of water is about 1,000 kg per meter cubed, or 1 gram per centimeter cubed. The bulk density, dry bulk density of soil is about 1.6 gram per centimeter cubed, or 1,600 kg per meter cubed. And then density of rock is about 2.6 kg per meter cubed, 2.6 gram per centimeter cubed, or 2,600 kg per meter cubed. So those are the three key numbers. Okay, you want to keep in mind. Okay, now this is for the three-phase system, right? And things don't change. And now let's take a simpler system, which is a two-phase system. When the soil is saturated, so remember we started with this phase diagram, right? Three-phase phase diagram, which has got a gas phase, water phase, and soil phase. Okay, when the soil is saturated, what happens? The gas phase is gone. Okay, so in a McDonald Coke cup below the Coke level, there is no gas there. So the gas phase is gone. So it's a two-phase system.
Carbonation.
Okay, yeah, no dissolved gases. That's a good catch. You're going to ignore the dissolved gases. Okay, that's chemistry, guys. We'll stay away from that. Okay, a B gas, the volume of the gas trapped in the system is 0. So what you have is two-phase system, which is water and soil phase system. And so again, I can put the same definition: volume of water, volume of soils, mass of water, mass of soil, total mass, total volumes. And again, I can simplify these formulas. Again, this is common sense essentially. A porosity is just now in this case is volume of the gas plus volume of void plus V, and the gas is 0. So porosity in a saturated system is simply defined as volume of void divided by V, because gas is 0 really. Okay. Similarly, you can define saturation ratio is equal to RS is equal to VW by VV. Again, and RS is always 1 because VW, volume of void, is basically equivalent to volume of water because it's all filled with Coke. Okay. And using these formulas, you can derive few other formulas. I'm not even sure whether I should do this, but I'll go give it. I think some of your problems need these things. So here's some formula I derived. This is all pretty straightforward. Porosity can also be defined as V minus Vs by V. What is Vs? V is the volume of the solids. Okay, so if I took the total V and subtracted the solid volume from it, and then divide by total volume, that's also another definition of porosity, right? Common sense again. Okay, and now I can substitute take the V out and make some math manipulation to define porosity is equal to 1 minus Vs by V. Okay, because I can divide V is 1, and so 1 minus Vs by V is another. So depending upon what's given in a problem, you should be able to manipulate these equations to get this thing, estimate these things. And we also know bulk density or dry bulk density of soil is mass of solid by total volume. And then I can substitute that and get another expression for V as mass of solid divided by bulk density will give you the total volume of the system. Okay. And also a definition of a mineral density is mass of solid by total volume of the solids, from which I can get the volume of the solids. And then I can take these two expressions and substitute into this porosity equation. The goal here is to, if I have the bulk density of this dry soil and the mineral density, I can get the porosity of the matrix. Okay. In fact, that's how we usually evaluate the porosity. Okay. You take the soil, dry it up, and find its bulk density, which is rho B. Okay. And the mineral density is the rock density, which is roughly 2.6, or we can estimate that. And then if you get those two, you can also evaluate the porosity. Okay. So how does that formula come from? It actually can be derived from some basic analysis of the formula we already did. So nothing magic about it. So you would see in the textbooks these formula, like for example, but it might look kind of hazy because this is not intuitive though. This formula is never intuitive. But previous formulas are intuitive, but by manipulating those intuitive formulas, you should be able to get these derived equations. Okay. And I hate to give these formulas, but I think one of the problems you'll be doing would require this. Okay, so let's do a quick problem. Okay. Gotta zoom these things. Okay. Can you guys read this? A field survey indicated the volume of the core sampled is about 75 centimeter cubed. Okay, and I weighed this core. It weighed about 150.79 gram. Okay, the weight of the core. And then I saturated this core with water completely, and then I weighed it. I got this weight. Okay. Then I dried it. I put this core in the oven and dried it, and the oven dried weight is this. Okay. Oh, I got to zoom this. Okay. Oh. Screwed now. What did I do? Oh. Okay, I'll write it up. That's easier. Okay. How do I zoom this thing? I'll figure it out at the end of this class. Okay. So what I did is basically I went to the field and I drilled a hole and took a core here, okay, somewhere. And it's actually in the unsaturated zone. So the saturated zone is here. So this is the unsat core. So I got a little soil core and the volume of the core, and then I found the volume of the core and everything. So the volume of the core is 75 centimeter cubed. Mass, then I weighed it, this whole thing. Okay. And then what I did was I wetted this core. I put some water into it and completely saturated this core, filled all the void with water, and then and that becomes wet or saturated weight is equal to 152.67 gram. Okay. Then I threw it in the oven and dried it. So the dry weight is by the way, this is how you evaluate soil properties. Okay. So the question is find n theta v r s rho b and rho m. Okay. Okay. So let's put some terminologies. What are we to these things? Okay. So when I evaluated the volume of this thing, that's the total volume, right? That's my v. That's my v in all these formulas. Okay. Now the next thing I want to find is the void volume, right? So how do I find void volume from these things? Let's try to do it. How do I find void volume? Any idea? So the porosity, first thing is if you want to find porosity, I know n is volume of the void by total volume. Total volume is known. So I know 75 should go down. What's the void volume? Can I calculate void volume?
2.4.
Well, part of the deal is to find porosity. I mean, so I mean, 0.4 is a average number, but each soil it will be different, slightly different. Okay. So that's why you do this test. Actually, you get cores and actually, in fact, this is exactly a test you would do. How do I find soil properties? You go and get a core and find the volume, find its mass, and then you saturate it, find its mass. You throw it in the oven, find its mass, and then you can calculate everything. You guys do this in geotech, probably? Yeah. Okay. So how do I get VV?
Well, you have the saturated mass and the dry mass. So the difference of the two is the mass of the water that fills the voids.
Very good. Yeah.
And you know the density.
That's one way to do it. Yeah. Okay. Is there an easier way there? Yeah. So you know the mass. Well, it's trivial, really. Okay. So why don't you take this problem and kind of play with these formulas which I give and evaluate, and I'll go ahead and give the answer. So n should be, actually this is a worked out problem in your textbook, so I'm not going to waste my time on this thing. So this is your first kind of play with these formulas the deal, okay? So go ahead and kind of think through this problem, think through all these formulas. So before you come to next class, at least I want you to have some feel for all these parameters. What is the porosity? What is the bulk density? And how do you calculate this? And this is a good problem to start with, okay? And this, as I said, is a worked out example problem in chapter 6, I think. So we are actually starting with chapter 6, and then we'll kind of go backwards, kind of odd way to do things. But the book is organized. I don't like the organization of the book. So we will. So go ahead and look into this problem and kind of figure things out a little bit. Let me go through the homework problems we have. Let's make sure what are the problems you can do. I think with these definitions, you should be able to do problem 1. Problem 1 in chapter 6 is very similar to this problem, actually. Okay, it's very similar to example mechanical calculation of these porosity and density and everything. Chapter 3, problem 3, I don't even know exactly what those problems are. I need to look at it. So you should be able to do problem 1, get it done before you come to the next class. By the way, this homework will be due. When will it be due? Let's make it not next Tuesday, the following Tuesday. So you get like 3 lectures on this. Okay, so we'll go easy to start with. Okay. Now, but you should be able to do problem 1. Problem 2, as I said, I don't know whether I covered it or not. I'll take a look at it. Problem 3 also you should be able to go ahead and read problem 3. See whether you can. Let's think through problem 3. Oh, Okay, I need to make a copy for you. I don't have one. Oh, did I?
For me? Oh, I have one.
Oh, you have one. Okay. Oh, you got an extra. That's what I was. That's okay. Okay, go ahead and read problem 3. Okay. Problem 3 is basically, I took a little box. So I took a rectangular box. Okay, and I'm packing it with balls, spherical balls. So this is the ideal porous media, right? And the box is cubical box, so it's 80 centimeter by 80 centimeter by 80 centimeter. Okay, and tennis balls of radius 4 centimeter, which means the diameter would be 8 centimeter, which means how many balls I can pack? How many balls I can pack? 10 balls, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So I'm going to, each way I can pack 10 balls in a row. So I'm going to throw a bunch of balls into the system and beautifully pack it. By the way, this is in crystallography, this is called cubic packing. You take a little balls and pack it. The goal is to actually say symmetrical box. Okay. Well, first of all, if I did that, the question is, what's the porosity? What do you think is the porosity? Close to 0.4. Don't say exactly 0.4, close to 0.4. Okay. But in this case, you can actually calculate the porosity, right? How can I calculate the porosity? Well, if I know the radius of the ball, I know the volume of the ball. Okay. And then I can calculate if each row can accommodate 10 balls. You can say how many balls I can fit into this box. Figure it out. Okay. And then I know if one ball has got certain volume, I can figure it out how many balls, all these balls would have occupied how much volume. And then the total volume of the box is 80 by 80 by 80. And so volume of the void, from these two volumes, I can calculate the porosity. Okay. In fact, this is the theoretical porosity of a spherically packed uniform beads, uniform glass beads or uniform porous media. Okay. Now here's an interesting question. What if I reduced, so this is what do I do? Yeah, my fourth problem is, if the same box was filled with uniform sand or grain of 1 millimeter. Okay, so you can think of a tennis ball with 1 millimeter. You don't have a tennis ball with 1 millimeter. Okay, let's assume, and that's my soil bead. So now it's the same box. It's going to be packed with smaller balls, if you will. Okay, what do you think will happen to the porosity? Go up or down? Down, 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 down. Richard? Say the same. Down. Majority wins, right? Always. Okay. Here's a good example. Okay. Do not go by majority. It doesn't matter what the issue is. Okay. So if you picked based on the majority, you actually lost. Okay. Now minority is same. It's. I'll let you figure it out. Okay. I can only say the majority is wrong. Okay. So I don't want to give the cat out. Okay. And that's a cool problem. So this should make you curious about this problem, right? But you are intuitively, and also the intuition can be wrong, right? You are right. Intuitively, if you thought, yeah, instead of tennis balls, if you put a smaller ball, the porosity should go down. No, wrong. The majority would say it'll go down. No, wrong. It's more than that. Okay. And before you come to next class, I want you to figure that thing out. Why it doesn't go down, and what is the real answer? Okay, so solve problem 4 before you come to next class, and you will have a beautiful intuition for this whole porosity and void issue. Okay.
In practice, those smaller particles are going to make the porosity go down, though, right?
Say that again.
Like in reality, like not this problem. Like if there's
Well, this is pretty much a reality problem, right? Well, nothing wrong, difference between this and reality problem. It's a
Like,
fine
I
sand.
think I understand why, but if they were smaller, would they pack in together and have less air? Then
We'll talk about it in the next class, okay? So we'll pick it up from this point, okay? So here's a box packed with tennis balls, box packed with tiny tennis balls. I want to know what happened to the porosity. In fact, you should be able to calculate exactly the number, okay? So come back with that number for me.